This is a topic that, of course, we're not going to get much practice in before the midterm. So it won't be a heavy part of the midterm. I might have like a multiple choice or something just to reward, in particular, those of you who are here right now. But so I'm not trying to stress you out, but definitely this is the direction we're going after the midterm and in the homework that sort of crosses the midterm. So it always happens. Okay, so we're going to talk about a problem called SAT. And okay, this goes back to, Boolean logic, which we've seen a little bit before. So as you all know from programming, right, the main operations are and, true and true, or true and false, or, and not, negation. True becomes false, false becomes true. This you know, right? So, for example, exclusive or, is exactly one of these two things true? That can be broken down into ands and ors and nots. Okay? So each of these formulas I can draw out, one of these trees. So, okay. So here's a more sophisticated one, which once took me a fair amount of time. So I can imagine a circuit where I have 4 bits, x1, x2, x3, x4, or a formula, and it's at some level simulating addition. So it should return true if x1 plus x2 is equal to x3, x4, and false otherwise. Okay, so 1 bit addition. And so you can, here would be a formula, which I guess is probably hard to double check yourself, so you can, it's more impressionistic. But this is expressed in ands and ors, and we'll do this kind of verifying arithmetic for you. Okay, binary arithmetic. So, okay. Then I drew it out as a tree. So if you wanted to draw it as a tree, right, you have sort of these 2 parentheses up at the top, and then it's connected by an or. So here's like an or at the root, right? That's this or here between the brown and the 2 outer parentheses at the top. And now, I can write the left-hand group as a subtree like this, right? So I'm taking the and of x1, x2, x3, and not x4. That's exactly what's written there. And then the right-hand side will come out something like this. Okay, so this is just visualizing the formula from kind of working top down. Okay, so Boolean algebra seems very limited, but with a little practice, you can do more than you might think. So suppose I wanted to encode as a Boolean formula the expression z is equal to x. So what does that mean? That means you have 2 Boolean variables z and x. It should return true if z is equal to x and false if z is not equal to x. And I want to write that out as a Boolean formula. All right, how might I do this? Sorry? Okay, z and x. So if z is true and x is true, this will return true. So a parentheses around this, presumably. Or not z and not x. Right? So if both z and x are true, this will return true. If both z and x are false, then this will return true. And in that way, you can kind of do something like assignment, right? The only way to make this formula come out true is to have z and x equal to the same value. Okay, how about an if-else statement? If x, then y, else z. Okay, so if x is true, then our formula should return the value of y. If x is false, it should return the value of z. All right, let me restrict you to Boolean algebra. So you can't use times. Okay, x and y. Is that what? Parentheses, I guess. Sorry, what should I write? Not X and Z. Okay, so if X is true, okay, then the second clause is going to be false immediately because X bar is false, so you won't get this. So if Y is true, it'll return true. If Y is false, it'll return false. So if X is true, the second clause is useless, and you're left with returning the value of Y. If X is false, then this first clause is always going to be false, so it's going to go to the second. And then if Z is true, it'll return true. If Z is false, it'll return false. Right? So you can do assignment, you can do if else, right? So the point is that, these three operations are actually pretty expressive, right? Once you start putting together some of these, small things, you can imagine building more complex things over time. In fact, the way I figured out how to do adding 2 bits is, if I can do assignment and if I can do if else, then I can add 2 bits. Okay. So let me introduce then the problem we'll look at next time. Okay. It's a very simple problem. You're given as input a Boolean formula with n variables and like total size m. So just count up all the symbols or something as size m, say. And your goal is to decide if there's some way to assign true or false to these variables so that the corresponding output is true. Okay. So that's it. So I just give you a formula and I say, can you make me happy? Can you make the formula true? Okay. Now, what I want to point out today, this will be my second to last point, or maybe my last, is that this is sort of like a search problem. What do I mean? I mean, if you get the answer, you know it's real, right? So when you look for something, the key property is that you can recognize it when you find it, right? Which is the case. If you find variables that evaluate it to true, I could put it into the computer and check that it's true. So in that sense, it's a search problem. So at the very least, there's a brute force algorithm where you try everything, okay? But it seems like a much harder search problem than the over-under game we did in the very first day of class. Okay, so that's the big question that we're going to start looking at. Is there a polynomial time algorithm for this simple problem? Okay, so that's where we'll start the discussion next time, and I'll end it there. Is there a polynomial time algorithm for SAT? All right, thank you. So we're discussing this problem SAT, which is really made of elementary parts, right? Just Boolean operators. And yeah, there's some examples. You can imagine these formulas as a tree, right? And in fact, while Boolean operators might be very simple, you could do more with it than you realize. Maybe at some level that's not surprising since we have computers that can do amazing things that fundamentally, down at the bottom, is just doing Boolean logic. So this is the problem that I introduced, right? Which seems perfect for a computer. I give you some kind of Boolean formula, x1 through xn. Takes n bits, x1 through xn, and outputs either true or false, right? It's very easy to evaluate a formula. For example, we could use, it doesn't matter. And the question is, does there exist something that makes it return true? Okay. So this could be, you can imagine this being very useful. I don't know, does my program have a bug or something? If I could write that down as a Boolean formula, then you'd have some kind of bug checker. Okay, so I kind of rushed through this for lack of time, but now we have more time. So here's a very simple formula with just two variables. Does this formula have a satisfying assignment? Something that makes the output true? And if so, what it is? What is it? Sorry? No, why not? Yeah, so I think expanding out, this actually has every configuration of the two variables, x1 or x2, x1 or not x2, and something like this. So no matter what you set x1 and x2 to be, there'll be some bad combination, one of the four combinations that's going to make it false. So this one's kind of unique because actually there's a compact explanation for why it can't be satisfied, but that's really more an anomaly. Okay, but it's just a warm up. Okay, so, right. So this is also an example of a search problem in a general sense of the word. You're looking for something. I mean, we're often looking for something when we do problems. But the key feature is that you can recognize the right answer. So if you're looking for a satisfying assignment and you think you found one, you can test it by just plugging it in and evaluating the formula. So that's how I'm defining a search problem in a general sense of the word. Okay, arguably many of the things we've done are search problems in this sense. But of course, that means you have a brute force algorithm. So there's always a finite algorithm. You can just try everything and see if one of them works. But it seems a bit trickier than the over-under game that we did in the first class, right? Like, I don't know, can anyone think of an algorithm or some ideas for an algorithm for this problem? I give you a formula, you want to know if there's a satisfying assignment. Yeah. Well, okay, sorry. A polynomial time algorithm. Yeah. Yeah, can we look at this tree? I mean, it seems tempting, right? So, like, what would the first step? I mean, I can zoom in on that tree if you want. Like, you have this kind of formula. Remember, you don't know what this formula is supposed to mean or something. You're just looking at this input. You've parsed it. You've broken it down. It's in your data structures. Like, what might you do? Okay, I can try assigning x1 to be true. Oh, the top one has to be true. Sure. Okay, so now you're faced with a decision. This is an or. So either this has to be true or that has to be true. Well, okay, so let's say you recurse. Okay, but you could recurse and say, is there a way to make this true, or you can make a way to be that true, or something, right? Um, right. Okay, this one might seem simple because you can just set this accordingly, but um, okay, okay. So let's say you're at an and. Now you need to make both of these sides true. I realize this side's kind of easy to deal with, so it's not a great example. But I'm looking at this and over here. Now you're saying I have to make both sides to be true, right? And if I did recurse, so you can't necessarily just, okay, let's say I have an and, I know both of my subtrees have to be true. And I say, oh, recursively solve this and recursively solve that, right? Find a satisfying assignment for this and find a satisfying assignment for that. That sounds pretty good, right? But what's the catch? So each of these trees could have the same variable in it. Oh, so I could say, okay, solve this, and then I could plug that in here and say solve the rest. But I mean, you have to hope to get lucky in the sense that, because you're trying to solve this without any consideration of the effects over here, right? That seems to be giving up a lot of important information. So in general, it's not, it seems trickier compared to like binary search or some of the more structured problems we looked at to come up with a good strategy for this problem. Even though at some level it would seem very simple. Boolean algebra is very simple. It seems simple than American shortest path or whatever nonsense I put on the homework, right? So, uh, there's no 5x plus 8y. But anyhow, this is sort of a big question. Is there a polynomial time algorithm for Boolean formulas? Okay. It's very tempting because it's like, isn't this exactly what computers should be good at? Like, you got everything down in Boolean logic. Shouldn't this be perfectly easy for a computer? You can imagine writing a brute force algorithm is pretty straightforward for this, but the brute force will be slow. Okay, so that's the big question that we're going to kind of think about a lot going forward. Uh, yeah, I guess we kind of had some discussion about ideas, but maybe I'll present it more generally. Does anyone have more ideas or suggestions, either pro or against, yes or no, for this question? Yeah. Okay, so can we do a bottom-up approach? Can I focus on the leaves? Well, okay, sure. Well, you get to choose them, x1 or x2, right? So it is a decision. And of course, x2 is here and x2 is there and x2 is here and stuff. Um, so somehow, uh, so yeah, you start at x1 or something. But then what would you look at? Like, how would you even? So it's an interesting question. So, okay, so I tried putting together like a high level pros and cons list. Why maybe you could solve this or why maybe we couldn't. And you could tell me if you think they're reasonable. This is just like something I made up, right? There's nothing true about this. So, okay, pros. Boolean logic is very simple. It seems perfect for computing. This is like what computers are for, to sort out Boolean puzzles, right? This is not ChatGPT like able to do your homework. This seems like exactly what a computer is for. I don't know if it can actually do our homework, but it hasn't so far. And in particular, it's very easy to evaluate Boolean functions. Okay? So I think those are pros. Cons, does anyone want to suggest cons? Why we shouldn't expect an algorithm? Question we haven't really asked before in this class. Yeah. But that's true of many of our problems. We're able to do shortest paths, and there's 2 to the n possible paths, or n factorial, really, right? So, because you can choose any sequence, and somehow we're able to figure out the best one. So often we're searching in a combinatorial large space, an explosion of things, but sometimes there's enough structure that we can actually pick a needle out of the haystack. Yeah. Yeah, it's hard. It seems hard to build some intuition for this. I agree. But somehow we can't give up on problems only because we suck at them. Uh, yeah. Well, I can look at continuous relaxations, but that won't give me the exact problem. Whatever continuous problem you write might give you a continuous solution. And then you have so you'll be solving a different problem. And then if you want to convert your continuous solution, this is a little beyond the scope of this class. Like I discussed this in a randomized class. You might try to take your continuous solution as a hint to solve the discrete, but that doesn't mean you're going to solve the discrete one exactly. All right, here's a couple or any more. All right, here's a couple of cons. Maybe well, let's see what I came up with. So the first thing that worries me is that as pointed out, Boolean logic is actually quite expressive, right? We can do assignment, we can do if else, we can do like adding things up, right? It's basically a programming language, right? You can imagine in the extreme over time being able to basically write a complicated language, I mean program, and saying, is there any way to make the algorithm output, the program output true, right? But the fact that Boolean logic is very expressive to me sort of counters the claim that it's very simple. Yeah, it is simple, but it could express a lot of complex things. So maybe it's, that's one thing I'm concerned about. And then maybe another is like, would it be too good to be true? Right? If we had an algorithm to solve this formula, could I describe the cure to cancer with a Boolean formula and then just give it to the algorithm, right? It's just maybe take as input like an image of a cancer cell. That's bits, and it should do something, right? So the idea that you can find a good algorithm to solve anything that can be expressed in Boolean logic would be amazing. All right, so that's maybe one concern. If it's too good to be true, this isn't an AI ML class, so if it's too good to be true, then I'm a little worried. Okay. Um, okay, so we don't actually know an algorithm for this problem. But people think about this a lot because if you have a good algorithm, then this would be a very versatile tool. And people nonetheless develop heuristics for this. They just make algorithms that try to solve it and try to find some shortcuts, and there's a big business of this. But provably, we don't have an algorithm that actually works. We also don't really have a clear reason why, although we'll develop some reasoning in this class. Okay, fine. So if Boolean satisfiability is too broad, what about special cases? So let me give a special case. Right. Okay, so here's a particular special case of Boolean satisfiability. It's a formula put in what's called conjunctive normal form. Okay, so that means like I have these clauses that are like x1 or x2 or x3 in parentheses and something 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 or something or something and something or something or something and so forth. Okay, so whereas before we had some kind of deep tree and stuff like this, if you drew out the tree, it's always going to look really flat. Just going to be an and of ors, no depth, right? It's quite reasonable to say, oh, if that depth, I look at the structured case with low depth, okay, can I solve this special case? Okay. So for this special case, does anyone have any ideas? You have to choose one of these three. Yeah, I mean, at least one of these has to be true, and at least one of these have to be true. But even then, if there's like m clauses, then you're going to have, and if say there's three in each one, you're going to have 3 to the m choices. It's a little tricky too. Yeah. Okay. Well, that would be amazing. So how do we do that? Well, let's explore that. Um, okay. So sorry, I should have said this first. Okay. So the more modest question we're going to look at is for a special case of conjunctive normal form, can I do something? Okay. Um, so at some level, okay. Actually, let me go back. I'll come back to this. Okay, so one of the things that sort of raised the alarm bells for me last time was when I realized we could do assignment and if else with sat formulas, right? So can we do something like that? Can I also get assignment and if-else statements uh, using just CNF form? Okay. So, for example, we'll start with assignment. So this is not in CNF, right? Because this is an OR of ands, right? So, but can we come up with a CNF that returns true if and only if z is equal to x? Any ideas? Yeah. The three isn't relevant. It's just it needs to be an and of ors, whereas this is an or of ands. Okay, we can do De Morgan's law. So you can do things like this is going to be equal to z and x. Well, maybe I'll write it this way. So it'll be equal to z. Uh, oops. Or z and x. I mean, just doing De Morgan's law one step at a time, and hopefully I do this correctly. You guys can correct me if I'm wrong. X or z bar and x bar. So if I did this correctly, this is like some kind of distributive law for Boolean algebra, right? So you gradually kind of invert and turn the and of ors into ors of ands, okay? And then you kind of do it again. Uh, right, so then you're going to get like z or, no, that's not right. Okay, wait a sec. Okay, yeah, that's fine. Z or z bar and z or x bar, that's applying De Morgan's law inside this left family. But I mean, this is the usual kind of Boolean. Hopefully you've done something like this before. Uh, X or Z bar and X or X bar. Okay, so this is just kind of distributing the logic. And then two of these are redundant, like Z or Z bar is always true. X or X bar is always true. So you get rid of these and you're left with Z or not X and X or not Z. Okay, which is like, I don't know, a little bit harder to guess initially. But you could start from the easy formula and then work your way down. Okay. So there I've written a little bit more cleanly. We can also do if-else statements or try to do if-else statements. So what we did before was like this. So if we applied De Morgan's law or we kind of factor this thing out, what do we get? Sorry, oh, okay. Oh, sure. X or not Y? X or Y? Oh, I see what you're saying. Yeah, that's my handwriting's bad. Okay, I'll just I already did this. Maybe it's not so interesting to do. Okay. So just a couple steps at a time, you're going to get X or X bar and Y or if you do it twice, you end up getting all the cross pairs. So you're going to get X or X bar and Y or not X and X or Z and X or not. Okay, I'm just reading it to you. One of these just disappears because it's redundant and you get something like this. It's a little bit harder to interpret, I think, compared to the original one, but it's in conjunctive normal form. So you come to a similar conclusion because of De Morgan's law. You can argue that CNF is also very expressive. I can do assignment, I can do if else. in conjunctive normal form. Okay. All right, so at some level then, we recover the same pros, cons list to some extent, we also know that the formulas are also very expressive like before, but maybe under the cons category, I'm less confident about this aspect. It's still not totally obvious to me that conjunctive normal forms are actually that general. The previous exercise just gives me some intuition. Okay, so here's what we're going to show, which is sort of a different kind of result than we've seen before. Okay, so the question is, can we get a good algorithm for CNF SAT? We don't know the answer to this either. Okay, but we're still going to say something precise about it. We're going to say that if you have an algorithm that can do CNF SAT in polynomial time, then you'll get an algorithm that can do Boolean SAT in CNF in polynomial time. The opposite direction is obvious. If you have a Boolean SAT algorithm, then you can just apply it to your CNF. The more interesting direction is you give me this special, nice, cleaned up, flat formula, and if you can solve these things, then you can solve anything expressed as a Boolean formula. Okay? So this is a good way to convince yourself that CNF SAT may also be hard. It might not have looked hard at first, but Boolean SAT was maybe more believably hard. So if you can solve this thing that you definitely think is hard, or at least you're more confident that it's hard, then CNF SAT should also be hard. Yeah. CNF SAT, it just means I give you the formula in CNF form. I give you a formula in CNF form. So it's a limited class of SAT formulas, of Boolean formulas. So Boolean formulas could be very deep, and you're only looking at the special case where it's kind of flat. It's this and of ors. So it's a special case. But we're going to show that the special case will get you an algorithm for the general case. Okay, so, all right, how does one even try to prove this? Well, what would one need to prove? Yeah. Okay, how do we do that? What? What are K-maps? So, okay, one thing you should be careful about. Okay. So, we could try to apply De Morgan's law all the way down. Okay? But actually De Morgan's law, so if you remember before on the simple example before, like you end up generating all the cross products, right? So in general, if you have many formulas and you apply De Morgan's law, you're going to get something exponentially big. So if you just do De Morgan's law all the way down, you're going to get, in the worst case, an exponentially large formula compared to the original size. So it does blow up your size. That was okay for, if else and z equals x and stuff on a small case because it just took a finite to finite, so the blow up's not that big. But in general, if I give you a big formula n, it can go to 2 to the n or something like this if you're not careful. So that's not exact. We do want to convert it, but you can't just apply De Morgan's law. It'll blow up on you in size. And if it gets too much bigger, then a polynomial time algorithm won't help you with the original one because it's polynomial time on a much bigger instance. So, okay. But we are going to try to do this. So here's what we'll do precisely. So here it's just important to see why this is useful. We'll come up with a polynomial time algorithm that takes a Boolean SAT formula and creates another CNF SAT formula with possibly more variables. That's one degree of freedom we have to work with. All I have to do is create a CNF formula, right? But I can do whatever I want otherwise. And the total size of this formula we're going to make is going to be comparable to the input formula. And it's going to have the property that the original formula is satisfiable if and only if the new one is. Okay, so if this lemma exists, if this algorithm exists, that would give us our original thing, right? So if I had a black box to solve CNF sat, I would take my Boolean sat, apply this algorithm we'll work out together in a moment, give it to the black box, and return that answer. Okay, so the emphasis is on is this conversion from the general to the special, and coming up with a good efficient construction for this. So two points that are important is that our construction takes polynomial time, because if it took exponential time, you wouldn't get a polynomial time algorithm when you put everything together. And the other is that the size is pretty similar. What really matters is that the size of the thing you make is a polynomial in the input size. It happens in this case, you can actually get pretty good where the size is roughly the same up to a constant factor. But in general, as long as the size of the new formula was within a polynomial factor of the previous one, then you still get this polynomial implies polynomial. Okay. So, okay, take this one. How could you convert this? How could you convert this to a CNF sat? And De Morgan's law is not going to help you in the general case. Maybe it seems like it would work here because it's sufficiently small, but in general case, it can blow up on you. So keep in mind that you are, maybe as a hint, you're allowed to introduce new variables. I'm trying to flatten out this tree. Well, how about a trick like this? Suppose, see, we're computer scientists, right? So we get to make stuff up. Suppose I introduced a new variable x. So let's say I want to kind of deal with, okay, this is depth 2. Let's try to figure out what to do with this subtree. So here's what we'll do. Suppose I could say, okay, I'm going to make a new variable called x5, and it has to be equal to the value of this intersection. Okay? And I'll set that aside and say, okay, that's a one requirement. And then I can put x5 here. So, okay, this has to be true. X5 has to be equal to the conjunction of these four things in this case. And this whole formula where I evaluate x5, which should be the value of this thing, that has to come out to be true. So I sort of ripped out one small chunk. Now I cheated, right? I wrote x5 equals and. You probably didn't think you were allowed to do this. So how would I actually do this in a conjunctive normal format? Yeah, or I guess what I'm asking is, so if I could do this and just say, oh, make this subtree always equal to x5, and then can I drop in x5 there? That would be very convenient. But how can I do this in conjunctive normal form? You're going to move this a level up? What does that mean? Like this? Oh, so at the end, I'm going to take these two, whatever, recursively, I can maybe try to deal with this or something. And then if I can put this thing into a conjunctive normal form, then at the end, I can take an and of these two things. That I agree with. But the question is, how do I just deal with this subtree in the bottom left? What happened? Okay. Yeah. So how am I going to, so let's say this is x1, there's some values, right? How am I going to force xy to be equal to the and of them? Let's just focus on this subproblem for the moment. Yeah. So yeah, I want to write x1 is equal to okay. So so you're saying I'm going to write x1. Okay, what should I write exactly? Okay, x1 or x1. No, no. So what I want to do is I want to introduce a new variable x5, and you write a CNF that says x5 has to be equal to the and of these. Let's say this subtree itself is already in CNF. But what I'm more interested in, how can I set the output and force it to be equal to x5? So you guys have actually done this once already in class. Yeah, how can I force the conjunction of these to be equal to this new variable x5 that I've created? Ah, okay, we know how to express assignment in conjunctive normal form, right? So I can write something like, in this case, uh, x5 is equal to, you know, so to say it's equal, if I look at this formula over here, then it's going to be like x5 or uh, x1 and x2. Oh, okay. Well, let me first look at a special case and I'll justify it in a moment. If I was only worried about two variables like this, okay, then we would be looking at something like uh, x5 or x1 and x2 and x5 bar or x1 and x2 bar and stuff like this. And if it's only two variables, now I can apply De Morgan's law and break it down. Okay, but we can do assignment. So the part I skipped is we should do a pre-processing step to first turn this into a binary formula that only has two variables in each. So that just means if it's an and of four, I just put two here and two here and it. So that's actually an important pre-processing step I forgot to mention. But then once you do that, we can take advantage of this kind of assignment, right? And then we can start introducing variables like, okay, x5 has to be equal to this, and I'll write down the equivalent conjunctive normal form for x5 is equal to x1 and x2. And I can write x6 is equal to this, right? So at some level, we'll sort of imagine taking this out and setting it aside. We'll write a few clauses that you have to satisfy. Now there's another variable x5, and your combination of x1, x2, and x5 has to satisfy the corresponding conjunctive normal form for this. Okay? So I kind of write that down, and then I drop x5 into this equation. And I do the same thing with x6, right? There's some kind of conjunctive normal form that says x6, and it'll be small, x6 has to be equal to the conjunction of x3 and not x4. And you write that down as a CNF formula. And you put x6 back in up here. And then here you say, okay, x7 needs to be equal to the conjunction of x5 and x6. You write that out out as as a CNF formula, just using our assignment and working through the De Morgan's law that we did. And you set that aside. Okay. And you put in X7. So if you can do assignment, then you can start doing some damage and you can rip all these apart. So at the end, you end up with like a bunch of these little CNF formulas, each representing one of these assignments of a couple things. And then you just, I have to satisfy this and satisfy this and satisfy this and. So it's really an and of ors initially, but then the two ands will flatten out and you get an and of ors. Okay, so that's the high level. So it's mechanical. And the trick is assignment. You take the subtrees and you just write assignment as a CNF. So I guess here I've worked through, I think I actually wrote a program to do this for me. Right, so what I've done here is I've listed out, so here's this saying x14 has to be equal to x1 and x2. And that's the conjunctive normal form that we would come up with for that assignment. This one is saying x15 has to be equal to x3 and not x4, and that's what you would get. Okay, so each of those, as you go through, will give you another collection of a few conjunctive normal forms. Okay, something of size, it's a little bigger, it's 10 times bigger or something, but it's within a constant factor. And at the end, now you have this big collection of things, and so you're going to just take the conjunction of all of them put together. Right? And then that will give you overall an and of ors. Okay, so once you can do assignment in CNF, you can start doing a lot. So for that reason, that's the construction. You can imagine turning it into a pretty straightforward algorithm. It might be a little bit annoying to go through cases, but right, it's a mechanical process. It's clearly polynomial time. And that's enough for us to see, oh, okay, I probably can't get a polynomial time algorithm for CNF stat because it's not so hard to convert a Boolean formula into conjunctive normal form. Okay. But it's a very interesting conclusion because it says, oh, even this nice instance is hard. All right, a more special case of this problem would be something called 3-sat. So 3-sat is just like CNF sat, with one restriction. You only have 3 variables in each of these ors, which in this context is sometimes called a clause. Okay, so if I told you there's only at most 3 in each of these, right? So you're getting a flat tree plus each one's going to be small. In the previous examples, it happened to be small, but that's not generally the case. Okay, so that's 3-sat. Next question is, can I solve this problem? It's even more restricted than before. Not only is it in conjunctive normal form, but there's only 3 variables in each clause. Earlier, there was a suggestion of, oh, does that mean we can march through the clauses and even just choose 1 out of 3, right? Like there's something about having a small number of variables in each clause, which is tempting. Oh, is this simple enough? Okay. So that's the question. Is there a polynomial time algorithm for 3-sat? Okay, maybe I'll take a vote to force you guys to pretend to participate. Okay, you have 3 choices, yes, no, and you're not voting. Okay, who's not voting? Okay. Who thinks there is an algorithm for this special case? Okay, and who thinks no? Okay. Okay. Oh, bummer. I'll just leave it there because it's better that way. Okay, we're going to show an analogous theorem. If you can get a polynomial time algorithm for 3-sat, then you can get a polynomial time algorithm for Boolean formulas. So 3-sat 2 we think is unlikely to have an algorithm. Okay. All right, so any ideas for how to prove this? Yeah, so it happened actually last time we did it. It did turn out to be 3-sat. There's two different ways to do it, but the high level idea is you're going to do the same thing. You can either start with, you already know how to go from a Boolean formula to CNF, and then you can go with CNF and just, the only issue is that you have large ORs and you want to split them up, right? So you have like x1, x2, x3, x4. There's 4, you need to get it down to 3. So I'll make a variable that says x5 is equal to x1 or x2. And then I can just drop in x5, x3, x4 or something. So you can use assignment to break up the big ones. Or it seems like if we look at this construction, especially because we did this binary pre-processing step, you also come out with a 3-sat formula anyway. So there's at least two different ways to go about it. The high-level technique is the same assignment trick. If you go through it, it won't generate more than 3 random variables if you're careful. Next time we're going to talk about 2-sat, but not today. Next time will be after the midterm. Okay, so I won't go through in much detail because the high-level idea is the same. You can use something like an assignment trick to convert any conjunctive normal form to 3-sat. So 3-sat is also, it turns out, just as general as a Boolean formula. I don't think that's obvious, before this lecture started. Maybe you've seen it before in a previous version of, if you've taken algorithms before, but I don't think this is at all obvious a priori. Okay, let me give one more. Yeah. Sorry? Yeah. Yeah, so maybe we'll go through it slowly. So there's really two steps in our construction. So the first step is to convert it first to binary form. Okay. So we need to check that both steps will not blow up the size of the input, right? Okay, so how can I argue that putting things in binary form isn't that big a deal? Because you might worry about introducing lots of intermediate nodes. Let me ask a different question. If a binary tree has 1,000,000 leaves, how many total nodes are in it? Really, n leaves, how many? Huh? 2n. Actually, you can do a little bit of 2n minus 1. But at some level, each of these nodes, you can think of like contracting and replacing 2 leaves with 1, right? Each one kind of reduces. So you start with n things at the bottom and you coalesce down to n minus 1, or to 1, right? And each of these binary nodes is reducing things by 1. There's n minus 1 node, internal edges in a binary tree with n leaves. Now we also have some knots, so you could have a knot in between every 2 nodes. You won't have 2 consecutive knots because 2 consecutive knots will cancel out. So you can maybe make a 3n or something. Okay, so in general, you're not increasing the number of total leaves, and the size of the tree is going to be roughly the size of the number of leaves. So in that sense, the size hasn't changed that much. Yeah, that's one way to look at it. So that's good, step 1. And now when you have one of these, now you have it in binary form. So I just have to look at, what happens when I assign x14 equals x1 in X2 or something, right? You're just looking at it and you're taking three symbols or something from your, a small part of your tree, and you're going to generate, I don't know, it might even be 20 characters long or something, right? It might be longer, but it's still a constant because there's only three things going in, and maybe an and or something, right? So, I mean, here it's actually drawn out, but yeah, this is definitely feels longer and more complicated than the original one. But I'm taking each of these assignments, each internal node in the formula is getting mapped to, I don't know, something of constant length, right? There's three clauses and there's only like 10 total symbols. So every internal node in the formula is getting turned into some constant size conjunctive normal form. And there's only, number of internal nodes hasn't changed that much from originally. So that's where the overall size staying the same comes from. Yeah, this is where the pre-processing step does help because they make sure that none of these individual things blow up by very much because you're only doing an assignment with a few variables. Yeah, I think it would have been more painful to work through if I didn't do the pre-processing. Then it might blow up a little. Okay, so I want to just introduce one more in the remaining time. So we mentioned circuits just a couple of weeks ago. We're talking about like DAGs and topological ordering. Okay. And so you might remember these slides. We have ands, ors, and not gates. Okay. The big difference between this looks a little bit like this looks kind of like what we've been dealing with, right? But there is one difference between this graph and the formulas we're looking at before. So this is not necessarily a tree, right? So this node has two parents, for example. That's the main difference compared to a formula. So this is on the other hand, usually, anyway, so it's more general than a formula. I can think of any formula as a circuit. Okay. Um, but yeah, I'll cut to the chase. So we have a circuit sap problem, which is now I give you a circuit. Can you find some way to turn on the light bulb, right? And again, one can argue that there's a polynomial time algorithm for circuit sat if and only if there's a polynomial time algorithm for Boolean sat. Here, perhaps we're going the opposite direction. Circuit sat feels more general. So the real question is, how do you take a circuit, a DAG, and turn it into a tree or a Boolean formula? Any ideas? But that will also apply to interior vert nodes and stuff like this. So that can blow up in size. But also well, it's not. This is not a good example, but this node could have two parents. Interior nodes can also have multiple parents. So if you're not careful and you just kind of factor it out, it will get exponentially large. But what else can you do? You're working from circuit to Boolean. As soon as you get this, you're all free to, yeah. So you have to be careful because if you start duplicating like at each level, then it's going to be like 2 times 2 times 2 times 2 times 2. It's going to blow up on you. Okay, you can do the same assignment trick all the way through. Okay, so you place every node. This is equal to some formula of the inputs. Okay, you can make it binary first, but the same techniques that we just did will let you take an arbitrary DAG and flatten. You even get a CNF. Okay. All right. So that is the point of this. So the point of this class was that here are some really basic and potentially useful problems. And what we showed in this class is that as far as polynomial time algorithms go, they're actually equivalent, which is a different kind of observation than we've had up to this point. Okay, so we'll do more of that after. One thing, so we don't have any official class on Friday. Do you guys want me to show up to just do some silly problems?